be about another collaboration, academic collaboration of types.
Thank you, Mark, for the introduction. Yes, so like the previous talk, this talk is going to be about a combination of research work and applications that came out of an NSF Frontier effort that is in its 5th year in the greater Boston area. So in some sense, this is like the same talk as last time, right? But with one big difference, that my title does not include the word privacy anywhere in it, and that's on purpose. So unlike the last talk and pretty much every other talk of this workshop, this is not actually a talk on differential privacy. So if you're a differential privacy aficionado and you were hoping that every single talk in the workshop would be about this, then I apologize. On the other hand, if you're truly a differential privacy aficionado, you're used to not having perfect accuracy. So this is sort of the noise, I guess. So my talk is called A Modular Approach to Cloud Security. I will describe what most of these words mean throughout the talk. Presumably you've heard of the word security before, but don't, at least I have no idea exactly what this word security means, but I'll describe to you at least what we're doing in this project. Let me start with the one word that I guess most of us might be familiar with, which is cloud, right? So cloud computing, or other people's computers, is a very nice innovation over the past decade of sort of giving anybody in the world the ability to store data and to make it available for anybody else in the world to use to spin up elastic computations, to do very, very strong number crunching at will from anywhere in the world and at very low cost. This is a very cool idea. Clouds are cool. Everybody likes having cloud computing or even having a cloud data center. So even all of us at BU and the greater Boston area have a production cloud environment that I'll mention later in the talk. But for now, what I want to talk about is sort of what exactly underpins cloud computing, right? So we have this very nice vision that we can tell to sort of freshmen or sophomores in an undergrad CS course about sort of, you can just sort of outsource your calculations to the cloud. But let's step back for a minute and think about, all of the amazing computer science and engineering innovation that went into building this thing that we sort of take for granted now, right? So we have all this complicated morass of software, of hardware, and of networking that makes all of this possible, right? So just to give a simple application, I could build, a web application running on a single machine in the cloud that, can connect to a web browser that runs on top of an operating system, that runs on top of some sort of commodity hardware. That is connected to all the other machines in the cloud and the rest of the internet via a network. And that's just like one machine out of the millions of them on the cloud. And furthermore, everything that I just said in the previous sentence can all be virtualized at pretty much every single level of the computing stack. So it's kind of a minor miracle that all of us were able to, as a computer science and engineering community, build something this complicated. And the key innovation that I want to argue that made all of this possible is the idea of modularity, right? So that there's no one person in the world that could describe to you how any sufficiently complicated computer system works, that all of us sort of work at different levels of abstraction. So I might be an operating system expert and I know how to build it, and I don't need to care about how, the details of how all the computer programs that run on top of me are going, what are they going to do? And I don't necessarily need to care too much about how the hardware underneath me works, as long as it satisfies a certain number of basic principles, and everything is all good, right? And the same of all the other levels of the cloud. But this isn't a talk about how to build a cloud. This is a talk about cloud security. So the question is sort of how can we secure something this complicated? And the short answer to this question is that we know how to sort of provide some small, like we can sort of prove things of the form or make very strong defensible claims of the form. Widget A in a complicated computing architecture has security property B, or at least can't be broken by attacks of type C. So I can show how different operating systems could be secure against side channel against attacks from different privilege escalation attacks will not work against certain applications running on top of the OS, or I can prove to you that a piece of hardware is sufficiently safe from side channel attacks, et cetera, et cetera. But how do I even know that all of these pieces, if I can even individually prove that they are secure, whatever even this nebulous word secure means, how do I know that in something sufficiently complicated like a cloud or any other sufficiently complicated computing architecture architecture that the composition of individual protocols gives us security of the overall cloud, right? So modularity was the key to making the correctness of the system work, and if all the individual pieces work correctly, then the system composes nicely. And the question that is sort of at the underpinnings of our project is, does the same process work for security? And the answer to this question is no. If you take a bunch of components that are individually proved to be secure, for most notions of the word secure, I'm leaving this word vague for the moment, that just because you take a bunch of components that individually seem like they're doing their job fine, they could destructively interfere with one another. And if multiple components are running on your computer at the same time, there could be some bug that exploits the interconnections between two processes that in some sort of standalone sandbox environment, either one of them would have been fine. Okay, so the goal of our frontier project, called the Modular Approach to Cloud Security, is sort of to resolve this ambiguity, and sort of as a pun that Ron Kennedy came up with is, to build security systems that, so rather than having the sum of the parts be a whole, it's instead like a holistic security guarantee. Okay, so this is a project involving a large number of researchers across 4 institutions, BU, MIT, Northeastern, and the University of Connecticut. And I can't describe all of the work done by all of these people, so I'll give a small subset of the stuff that we're trying to accomplish. And I'll, big caveat up front that the work that I'm going to describe is definitely biased towards the stuff that I myself am doing, just because I'm the one of the group giving the talk, and therefore I get to bias it towards myself. That's my right, so I'm doing that. Okay, so there are 2 components that I want to sort of 2 different halves to my talk. First, I want to talk to you about how we're doing work into building composable security analyses. So analyzing the security of various computing services in such a way that those analyses continue to hold even as each individual widget fits into part of a bigger ecosystem. And the second thing I want to describe, which is very different, is talking about a unique computing environment that we have in the Boston area called the Massachusetts Open Cloud, and how that can enable some cool new secure computing applications. Okay, so I'll begin with the first part of composable security analyses. So what we want in this project is to sort of move away from a monolithic computing environment that we sort of get with any commercial cloud provider today, Amazon, Google, Microsoft, whatever, in which everybody sort of, when you sign up to any one of those systems, everybody has sort of, the ability to use the same exact kinds of software. You have one of a relatively small number of images you can run, and all of the back-end cloud software is all whatever the company that gives you the cloud, like that rents you the computer, say Amazon or whoever, also manages all the software that underlies how the cloud works, and everybody must trust that company once and forever, and everybody gets the exact same kind of isolation guarantees from all the other tenants on the cloud and so on. And so what we want to do is move towards a world that's sort of maybe more economics driven, in the sense of every single tenant can sort of freely decide and flexibly change their decisions as to what kinds of pieces of hardware and software on the cloud they choose to trust, how much they're concerned about the correctness, about the timeliness or performance or efficiency of results, how much they're concerned about the privacy of their data and the isolation of their computing processes, and finally, to connect all of these together, the cost that they're willing to pay and where they want to apportion their actual dollars when they pay for for services on the cloud, and which of these features that they want more. Okay, the fundamental cryptographic tool that underlies our project is something called universally composable, or UC security, that I'll describe next. So UC security is a way of arguing that it's a way of sort of formalizing this, what I've called now, since now vaguely, this notion of security in terms of how do I know that a particular algorithm or application or computer program does what I want it to do. So the way that one can codify security in the language of UC is to say, take any application or computer program or algorithm. Anyway, take any. Let's see if this this works. No? Okay, never mind. So take any application or computer program in blue, and the hope in the way that this security definition works is that we can design some kind of specification that is hopefully much simpler and cleaner to understand than the underlying program, but that from the perspective of the rest of the world, from anybody looking at this program from the outside, the program and the specification are indistinguishable. So the spec, even though it's hopefully much simpler to understand and reason about than this complicated computer program, that these two things are sort of functionally equivalent, at least as far as the rest of the world is concerned. Okay. And so we'll say that a computer program is secure at least up to specification S if this thing is the case. Okay. So at least as far as how its input-output behavior works. But this definition is a little bit too rigid, at least at the moment, or too weak at least. At the moment, this sort of what I have described is not so much a security guarantee, but a correctness guarantee, right? Just that the specification and the program are functionally equivalent. This is sort of the domain of formal verification. This is what those, like the programming languages community tries to do, that they try to say, can I form some sort of spec in some higher level language that codifies, a C program or something, and that I can prove that these are functionally equivalent. But in security, we don't just care about the sort of I/O behavior, the input-output guarantees, but we also are worried about, what are the other ramifications of using a system? What are the sort of side effects that might spill out into the world as a result of me using this particular computer program? It could be the case that, if this thing is a piece of hardware, that it could be leaking side channel information like timing or power analysis. If this is a piece of software, it could be revealing, it could be interacting with other things in the world, and from looking at the transcripts of what it communicates with the rest of the world, you could learn information from it. So the real notion of UC doesn't just consider input-output behavior, it also considers these kinds of side effects and forces them to be part of your modeling process. So your hope is that your complicated computer program is represented by this specification, both in the way that it interacts with the rest of the world, both in terms of how the rest of the world sees it from an input-output semantics, and in terms of any side effects it spews out into the world. Okay, and so you want to prove that these two things are close. So actually, you don't want to prove that they're identical. You want to prove that the hope is that the specification is simpler to understand than the program. So you hope that there's some sort of translation mechanism or a simulator in the crypto parlance that can translate between them. And so this is how we'll define security in the language of universal composability. That some complicated program is somehow it is as secure as if we use some sort of simpler to understand specification if they're functionally equivalent, P and S are functionally equivalent, and there's some way to translate from all of the side effects that you see in the real world into all of the side effects that you see in the specification. And so the hope is that the specification is some simpler representation of the program. So this was like a super quick description of this complicated notion of universal composability. If you're interested in seeing more information about it, we have several hours of lectures by Ron that we've recorded and put on YouTube. Okay. So in this project, this modular approach to cloud security project, one of our big objectives has been to prove the UC security of many different components at many different levels of the computing stack. So we've proved the UC security of methods, of cryptographic methods to do database searches over encrypted data. Various things involving blockchains, how to do oblivious computing, which I'll spend more time discussing, how to do anonymous messaging so that you can route messages over a network so that nobody knows who's talking to whom, and protect smart contracts, again, in the cryptocurrency space, how to argue about the security of different operating systems, especially a unikernel-based operating system that we've built at BU that I'll describe a little bit later. How to understand and reason about the security guarantees offered by different pieces of hardware, such as trusted hardware enclaves. And finally, how to understand how the networking and the cloud underpinning infrastructure that connects all the machines together works, including this open source program called OpenStack that I'll describe a little bit later. And so we have all these widgets that sort of specify how these various kinds of applications work. And so we have specifications corresponding to some of these programs. And the specifications you should think of as a simpler way to understand what are the ramifications of using this program. And the specification basically includes includes a whitelist of any kind of security defect or imperfection that any one of these programs has, or any kind of prerequisite required to use it. So for instance, if you have a mechanism for protecting data using encryption, one prerequisite is that there has to be somewhere to store the cryptographic key material, right? And the security of the higher level database system depends upon that. And so it's relying upon some other mechanism somewhere lower, deeper in the stack to enforce that precondition. And the main reason, the benefit of proving all of these systems secure in this universal composability way is that then we can connect them together. So then we can do some kind of mix and match system to say, now if you're a cloud tenant and you want a system that I want to pay no more than X dollars and I want to make sure my data is confidential, then there may be multiple ways that you might want to go about doing it in the hope of having some sort of unified framework in which to reason about what all of these widgets do and do not provide, is so that then you can make a sort of a comparative analysis and an informed comparative analysis as to how you want to spend your computing dollars. So just to give one example of what I mean by this, so let me say a little bit more about this idea of oblivious computing. What I mean by this is that there's some cloud tenant C who has some complicated task that it wants to outsource to a powerful server on the cloud. And the tenant wants the cloud to compute this function for her without learning this input X. And there are many ways that you could go about trying to figure out how to, that you could go about trying to build a system that will obliviously compute the answer to this function in such a way that the server has sort of no idea what it's doing. So one example is to use a cryptographic idea called secure multi-party computation, which I will describe in much more detail later in the talk. But the punchline here is that it has some trust assumption that you split the information over multiple different machines and you trust that they do not collude. And as long as the different machines aren't all working in cahoots against you, the security of your data is protected as the client. There's a very different way of doing this calculation over protected data using trusted hardware systems like Intel SGX. Where the trust assumption then is very different. You trust that the chip sort of does the isolation that Intel says it does. And there's an even different method that I guess maybe we don't think about as much, but is probably the most common way that we use the cloud, is that we're just trusting that the cloud vendor is isolating our machine on the cloud from all the other machines in the cloud, and then we can just throw all of our data in the clear in that particular virtual or physical machine and compute the data there and then destroy the machine afterward. And trust that the cloud will isolate the machine from us. I mentioned this example just to say that these are sort of three ways of instantiating the problem of oblivious computing that work in very different layers of the computing stack and are designed by very different people who don't even often talk to each other. But by thinking about this from the standpoint of like what tangible problem are they solving, in some sense they're all solving the same problem. And if we can show that these are all instantiations of the same ideal spec, but that have different kinds of trust guarantees and expose that directly to cloud tenants, then we can allow them to see here are three different ways of solving the same problem. It doesn't matter to you that they use different technologies. What matters to you is that you want to pick which one you are willing to trust, which of these preconditions you're willing to trust, and also how much money you're willing to pay for it. Okay, yeah. So yeah, we want to put trust in the forefront. We also want to understand exactly how these security analyses work over complicated systems that involve multiple different layers. So I'll give you an example of this. So one of the applications that we're working hard to build in a cloud data center is to build a system that allows medical doctors to take fetal MRIs. So if you've ever taken an MRI before, you know that like there's one really important thing that you have to do when an MRI is taken of you, which is to remain still for a while, because an MRI is basically taking a bunch of pictures of you from many different angles. And so in order to make sure that those pictures are sensible to the doctors, to basically reconstruct sort of a 3D image from a bunch of 2D pictures, you remain still in the machine for a while. Okay, this is a problem when doctors are trying to, say, take the MRI of a fetus to try to see if there's any kind of medical abnormalities in the fetus. Because try as you might, a fetus will not stay still for you, right? Like, this is just not going to happen. So instead, if you want to take a bunch of 2D pictures using an MRI of a fetus and try to reconstruct them into a model, this has become a much, much more complicated computer graphics question of how to take all these different pictures and fit them together. And almost no hospitals have like the computing capability in order to run this kind of sophisticated computer graphics. And so what they do is they send it all out to other people to do this for them, and then they get the results back in a couple days. But what we want to do is to make it so that when a doctor wants to take this fetal MRI and combine it and form a 3D reconstruction of the fetus, that they can do so by just buying a bunch of computers on the cloud, or renting, I should say, computers on the cloud, and spinning up a bunch of these and do this massively parallelizable computation really quickly. But to do so, right, just to understand the security of this very, very privacy-sensitive information, medical data about a fetus, requires understanding the security also, the security implications of all of the things in the cloud that underpin it, right? The operating systems you use and the cloud management infrastructure itself and whatnot. And all of these pieces, I won't belabor the details of how these pieces work, but they all sort of have sub-widgets of their own. All of these pieces, so OpenStack is an open source system that a lot of cloud vendors use to orchestrate running the cloud itself. It's about 9 million lines of code. It's this very complicated system that has many, many pieces within it and sub pieces. And we've gone through the process of trying to understand sort of in this universal composability framework how to reason about the security of these open source systems like OpenStack. Yeah, we have a paper about that, which was, it took a lot of effort. It was like about a 100-page paper or something like this. And from this procedure, we've learned that using universal composability to prove the security of all these complex computing programs is possible, but is really, really tedious. And we learned a lot of lessons from this. And now we've started to go to the programming languages community to try to mechanize the act of formally verifying the security of computer programs using this tool called EasyCrypt, which allows us to prove in UC security that a computer program meets this specification, both in correctness and in terms of making sure we've whitelisted all of the possible security defects that it has. We've completed a case study of this that should be posted online very soon. So yeah, so through this process, the main thing that we've done in this program is to build these composable widget, these security analyses of all these different widgets so that we can compose them. But there's another thing that we've been working on, sort of on a different angle within this project, which is based on our collaboration with an organization called the Massachusetts Open Cloud. But I'll describe in the second half of this talk what this organization is. But first, let me tell you the problem that we've been trying to solve together with them. And the problem is to do secure computing on the cloud. So to give some examples of why one might want to do this, these are some actual things that we've talked about with people. So there are companies in Boston who want to compute the average salary to understand the pay disparity between men and women or across ethnicities, but without exposing salary data of any individual company. Or researchers in hospitals who want to understand sort of for diseases, what does an average case of a particular disease X look like? What are the markers of a particular disease? If a disease is rather prevalent, then the hospital has enough data from its own patients in order to understand this particular disease. But if a disease is rare, then no individual hospital has enough data to understand what is an average or typical case of a sufficiently rare disease. And as soon as you want to talk about data sharing across hospitals, then we enter the domain of privacy laws like HIPAA that we've heard about earlier today. So the question is, how do you do so? How do you come up with this like average case of a rare disease without revealing individual patient data? Or just the sort of the generic version of this, companies want to run some kind of data analytics in a public cloud, but they don't trust a single cloud provider. And the solution to this that I want to talk about in the remaining part of this talk is something called secure multi-party computation. And the upshot of the way that it's going to work is that rather than outsourcing, any company outsourcing its data to one public cloud provider, it's going to outsource it to two or more. Okay, so at first glance, this sounds worse, right? If you weren't willing to outsource it to one cloud provider, why would you give it to multiple cloud providers? And the answer is that we're not going to outsource the company's own data, but we're going to outsource some sort of encoded version of the data. We'll encode the data across multiple cloud providers. in such a way that the data is individually, or even small subsets of the data, of the encoded data, is meaningless for understanding exactly what the input information was, but that the cloud vendors can calculate over the data together to learn some kind of analytic. Okay, so I feel like most of the talks here have had either a definition slide or some kind of legal statement, so I figured I would fill out my bingo card in one slide and combine the two. So here's like a picture from an actual congressional bill in the last Congress, the 115th Congress. It's a bill called the Student Right to Know Before You Go. It would have, since most of us are in the educational space, the bill is about educational data about students, and trying to calculate interesting metrics from data about students, like what are the average salaries of future graduates based on which university they go to and which major they go to. There's all sorts of interesting data privacy questions here, but I don't want to talk about the bill so much as I want to talk about this one part of the bill which describes this technology that the bill requires for use when calculating these kinds of educational statistics, which is secure multi-party computation. So the definition says the term secure multi-party computation means a computerized system that enables different participating entities and participation of private data sets to link and aggregate their data sets for the purpose of performing these pre-approved computations without transferring or otherwise revealing this private data to each other or anyone else. So what this means is, we have a bunch of computing entities. These can be individuals or companies, entities that hold their own data sets. And they want to calculate some function. They want to jointly calculate some function of this data, but they want to do so in such a way without actually handing over their data to each other. Okay, so they want to do it as if they were somehow handing all of their data to some trusted black box entity that would just sort of be a sync of their data, and that would compute the function over their data that they wanted and hand the function result back to these participants, and no more information would be revealed. So they don't have this fancy sinkhole black box. So they want to somehow compute this function working with each other in such a way that they learn no more information than they would have if they had this box. Okay, so they just want to learn a particular function of their data and nothing else. I'll emphasize that secure multi-party computation, this definition says nothing about inference. It says nothing about whether this function is something that they should want to compute with each other or something that would reveal too much, that the result of the calculation would reveal too much of their sensitive inputs. So in this way, MPC is sort of independent of, but very complementary and synergistic with differential privacy. So you could imagine computing securely this any kind of differentially private metric. The MPC is about protecting the act of doing the computation over data held by different parties and making sure that that computation can be done in such a way that nobody has to share their input data with anybody else. And the differential privacy is about protecting the results, right? So these are sort of independent and synergistic questions. But for this talk, I'm only going to, like I said, this is not a talk on differential privacy, so I'm only going to talk about the MPC piece. So this idea of MPC, of sort of computing jointly over data that we cannot read and we don't have to share, is something that has been used in practice in a handful of occasions. I'll just specify two that we've worked on, but there are others in addition to our own work. One thing that we've worked on is actually calculating this pay disparity metric, the wage gap between men and women throughout the city of Boston. The most recent calculation we did in 2017 involved real salary data from about 167,000 employees in the greater Boston area, or about 1 in every 6 employees throughout the city of Boston. The results of this metric of sort of what is the overall citywide pay disparity, those reports are available on the City of Boston website. The underlying data of what are the individual employee and employer salaries, nobody knows, because that's the whole point of the system. So we could calculate the overall aggregate wage gap without knowing anybody's individual wage. Another system we worked on with a nonprofit entity called Callisto, inspired by the Me Too movement idea, is to build a system that allows survivors of sexual assault and violence to report their experiences in such a way that the information is cryptographically protected and unavailable for anybody to read, even the server providing the service, unless and until another person names the same perpetrator. This is is based on the idea that people might feel more comfortable coming forward and making sexual assault accusations if they have, if there's somebody else coming forward at the same time with them. So if leaving aside the social failures that lead to the fact that one has to feel like this, the point of the platform is to make it so that the information, this very sensitive information, is cryptographically inaccessible to anybody until two people come forward and name the same perpetrator. Okay, so I've named two different applications of this idea of computing, protecting data even while you're computing over it. There are a handful of other ones that I won't describe in this talk, but the fact that I can more or less enumerate all of the applications of MPC is kind of weird. This is a 35-plus-year-old technology. It seems like something that could be very useful, right? We protect data at rest all the time and in transit, but we don't protect data while computing very often, and it's a reasonable question to ask why. One answer you might hear often is the performance of this system, that it's very slow. And this is somewhat true, but it's changing very rapidly. So secure multi-party computation, even over the past half-decade, has gotten markedly faster for decently good settings in the sense of computing some reasonably not too complicated calculation, in this case the Advanced Encryption Standard, AES, over reasonably small-scale data with a reasonably ideal network is something that can be done within, this is a log-scale graph, nowadays it can be done within like an order of magnitude of computing over data in the clear. So performance of MPC is not usually the reason why MPC is a big impediment to use, but it's at least on small-scale data and relatively simple calculations. So MPC has this interesting property that you get sort of security of your data from the fact that the multiple servers that are communicating with each other are isolated, that they're all physically distinct, that there's no single attacker who can control all of them. But you get performance from co-location of your information. And this is because when you do MPC, you've sort of fundamentally traded off computing for networking. So you want to do some sort of joint computation amongst these participants. But in order to do so, you have to send a bunch of information to amongst yourselves. The information is encoded and unintelligible, but you have to send a lot of it. And as a result, you've sort of traded off, in order to do any sort of computation at sufficient scale, you need a lot of network communication. And so the faster you can do that network communication, the better that you'll be. And here's what comes into play, this cool system that sort of a sister project that we work with called the Massachusetts Open Cloud. The MOC is a production cloud environment. It's out in western Massachusetts. And unlike most cloud providers, which are controlled entirely by a single provider, the MOC has multiple different entities that build it. So it's a single data center into which anybody can go and rack and stack a bunch of computers and manage them. So there are many different commercial providers that we work with, including Dell and Lenovo and HP and Cisco and Brocade and Intel and so on and so forth. And many of them have a bunch of computers racked and stacked, right? So you have, and they're physically in different, within the same data center, but in different parts of the data center, like with like fences separating their own individual computer stacks. So, right, so you have computers administered by different people, by mutually distrusting and competitors, companies, but that are in the same physical data center. So you have really, really fast network connectivity, really high-speed bandwidth between mutually distrusting machines, which is exactly the right environment in which to run MPC. So we get both the performance and the security. Yeah, so we've spent a lot of effort as a security, as a cryptographic community to build MPC to scale, and we can make MPC run pretty fast in terms of the complexity of the analysis that we do. We can handle, in principle, any computation, but in practice, reasonably complex ones. We can even handle them with a reasonably large number of parties. There's a lot of security, a lot of crypto research into that. But data size is not usually something people think about. Usually we think about trying to run complicated analysis over small-scale data. But the distributed systems community has sort of gone in the exact opposite direction nowadays, right? They do a lot of work that's reasonably simple analyses over large-scale data. And so what we wanted to do with this project is to make it easy for ordinary software developers who work in distributed systems to make it so that they can implement secure multi-party computation and run it over our multi-provider cloud. And so we have this system called Conclave that does this. We call it Conclave. It's sort of like a secure enclave, but rather than outsourcing your data to one entity, it's sort of outsourcing it to a bunch of people who work together in order to calculate whatever question you want. So we have software available online and a paper. And the way that basically that the system works is that it allows anybody to accept, to input queries in any, like an ordinary SQL format. And it will run it on any existing data backend that you have, like Spark. And it will use any MPC engine that you have available to run it. And it uses a bunch of static analysis tricks to try to figure out can it minimize the amount of data that it has to process using secure multi-party computation while maintaining the security of a system. So just to give a simple example of, let me skip ahead here, of how a system might work. Suppose somebody has a calculation that they want to calculate a metric over many, many different people's inputs data. And the metric as a SQL query sort of looks like this. It has some concatenate operations and projects and sums and so on. The way that the system works, it uses a bunch of tricks to figure out how it can optimize this query. So for instance, it can notice that the first two operations in this particular query are a concatenation and a projection, and those two operations are commutative. You can do them in either order, and they're the same thing. So you can sort of switch the order of the projection and the concatenation, and the reason this is useful is that then every single entity can do the projection, the first part of this query, on their own. So this sort of box here represents the stuff that needs to be done using secure multi-party computation, and now we've kicked out some of the work from needing to be done there. We'll just ask each of the people who hold input data to do it locally themselves. The same thing is true of a concatenation and a sum, and so on and so forth. So now we can do even less work inside of the secure multi-party computation at the beginning, and also at the end, the final step that I had here is some sort of division by a constant, and that's a bijection. So whatever you would learn from viewing the output here, you would learn exactly the same thing from the input to that particular operator, and as a result, it also can be done in the clear. So it's a tool that basically just automates running like this process of sort of figuring out how can it minimize the amount of work that it needs to be done under secure multi-party computation. So we have this conclave software. You can the package is available on GitHub. We've also integrated in with the Massachusetts Open Cloud and also with the Dataverse system that you heard about on the last talk, which is one of the largest repositories of social science data on the web, to make it so that anybody can ask a query of information held in Dataverse, even to make a query over data that you maybe don't have the ability to read in the clear. Let me skip ahead. Yeah, so in summary, I've described a few distinct efforts within our Max project. First, that this idea of universally composable security that we've pursued can lead to modular security analysis of different widgets of the computing throughout the computing stack that can be composed to understand how complex systems work, and that it is capable of being formally mechanized and verified. Second, that if we have this unique infrastructure, this Massachusetts Open Cloud, it's this nice combination of sort of isolated machines, but very physically co-located close to each other, so we can do very fast, secure multi-party computation. And we have this software package called Conclave that has this some neat static analysis trick to automate sort of decisions of how to make the MPC software run as fast as possible. If you're interested in the stuff that I mentioned, I'll just give a plug. And if you're the kind of person who just likes to hop from workshop to workshop, we're running a workshop next week at BU to look at sort of these questions of secure multi-party computation, how to make it fast and usable and formally verified. Thank you.
Question? I have a question. So you, in the universal composability part, when you use EasyCrypt for verification, so how complex are these examples? And so if I understand well, the proofs are all interactive. How complex they are to make more automated?
So EasyCrypt itself is a package that allows you to prove, in principle, you can prove sort of any cryptographic, most cryptographic statements, and it can be formally verified with a very small trusted computing base, which is cool. It was not built to handle this definition of universal composability, and shoehorning UC into EasyCrypt was a giant mess. is the technical answer. So to prove the security, so what our case study was to prove the security of just sending like a secure message communication system, like just to send messages based on the fact that we have like a key exchange mechanism. So sort of compose the fact that you have like Diffie-Hellman key exchange in order to do secure message communication. A pen and paper proof would take, I don't know, a couple of pages. The EasyCrypt code was 17,000 lines of code, which is not at all feasible. But we learned from this that a lot of the reason that this thing was very big was that there's a few things that EasyCrypt sort of struggles with or is not used to, and it takes a lot of work to shoehorn in. But this work is like there are these very specific kinds of tricks that we had to apply over and over and over again. So we think that this is automatable.
From the universal composability aspect, or you think are more general?
It comes from sort of the impedance mismatch between the way UC works and the way that EasyCrypt is like built to handle. But we think that this impedance mismatch is something that we can overcome and that we're going to work towards. So because we just had to apply a few simple-ish tricks over and over and over again. And so we think that this process itself is automatable. So if we can build some sort of higher level abstraction that can then compile it down to this 17,000 lines of EasyCrypt code on its own, we think that this is possible.
Yeah, EasyCrypt doesn't provide really some tactical language, right?
It does. It is a tactics-based thing, but it's meant for...
You cannot write your own tactic, or can you?
Not easily, no. No, it's not easily extensible in that way.
When you were presenting your principle of universal composability, you were talking that, okay, this notion can deal with side channels as well, and then you were showing some slides. And then you show all these widgets at different layers of abstraction and connected them and so on. And I could think about a lot of side channels might appear because of the interaction of these components. Have you captured some of these side channels in EasyCrypt as well? And maybe if you can give me an intuition like how hard that was if you did it, or which side channels do you consider?
Right. So let me first answer the part about EasyCrypt. No, the side channel, like the EasyCrypt work was a simple case study, so it wasn't nearly as complicated as the pen and paper proofs that I mentioned earlier. Right. The side channels that we referred to are mostly like the kinds of information that are revealed in the act of doing the computing. So what kinds of network communications are you exchanging? So for instance, if you interact with a particular website and it gives you a token, and that token is used to authenticate you or to authorize a particular decision to be made, then who else has the ability to see this token? Where did it flow across the internet? And who else might then be able to use that to impersonate you? That's an example of a kind of thing that I mean by side channel. So I'm using the term much more generally than just like power or timing analysis kinds of things, right? Just sort of any information that you see throughout the course of doing the calculation that might potentially be useful to an adversary at a later point in time. This is my general notion of side channel.
You consider time attacks, for example, when you were using this principle?
Yes, in some of the analyses, yes. Yes.
Is it a system that is time secure, or is this system that is time secure? You put it together, and it's still going to be.
Right. So the system. Right. So the universal composability comes with a composition guarantee. The composition guarantee does not say that no matter what else is happening in the world, that your system will be perfectly safe. Because that's something else that is happening in the world could be that there's somebody out there in the world that's spilling all your secrets, right? Maybe you gave your secret keys to your best friend, and something else happening out there in the world is your best friend is posting it on the internet, right? So what it means is that you can easily reason about how the systems continue to play nicely together or not, how they constructively or destructively interfere when they're composed. It doesn't mean that definitely everything is okay. It means that you can understand how the programs, the complicated programs, interact just by understanding how the simpler specifications interact. If you look at how the specifications interact, if they interact nicely together, then you know the programs will, else you won't. Yeah.
All right. So let's thank Mayank again.